Welcome, and let's talk about the problem solving involving acids and bases. Question number 7, normally in a normal question paper. We have got a recent question paper here, which is 21 marks long. I'll just try to clarify a few things. The first question, they say dissociation constant of some substances given in the table. We are given 3 substances there: hydrogen sulfate ion, ammonium ion, and hydrocyanic acid. Now write down the name or formula of the substance that has the highest tendency to dissociate. Give reason for the answer. If you look at the Ka values there, the one with the highest Ka value will be hydrogen sulfate ion. So that our first answer will be hydrogen sulfate ion, because we know that the ion or acid with the highest Ka value will be the strongest one. So which means will have a highest tendency to dissociate into ions. Now the reason will be it has the highest Ka value. That's the first question. The second question, that is 7.1.2, they say write down the formulae of the conjugate bases of hydrogen sulfate ion and hydrocyanic acid. Hydrogen sulfate ion, we know the conjugate base of it will be a sulfate ion, SO4 2-, and for the hydrocyanic acid it will be just 1 hydrogen less, which is Cn-. Now we go to 7.2.1. According to this one, they say to us, now is a long statement: to determine the percentage purity of sample of oxalic acid, the 3 steps below are followed. A standard solution of sodium hydroxide is prepared by adding 50 cubic centimeter, underline that, of sodium hydroxide of concentration 0.63 in 950 cubic centimeter of water. We've got 2 volumes there added together. An impure sample of oxalic acid is prepared by dissolving 0.25 grams in 75 cubic centimeter of water. No problem. Step number 3, the oxalic acid solution is titrated with the sodium hydroxide. During the titration, we are given now 40 cubic centimeter of the original solution of sodium hydroxide is needed to neutralize 50 cubic centimeter of the impure out of the 75 oxalic acid. The equation for the reaction is given here. Now they are telling us to say the first one, define endpoint of a titration. Endpoint is normally when the color of the indicator changes. So point where the indicator changes color, or in this case, fine, 7.2.2. So is a point where indicator changes color. 7.2.2, they say calculate the concentration of the standard solution. So the standard solution is prepared by adding 50 of the solid of the solution of sodium hydroxide to 950, and that the first volume of sodium hydroxide will be 50, and the second volume of the diluted solution now with a known concentration, that's what we are calculating, it will be 1000 cubic centimeter. So we are using dilution here, so we can just write C1 V1 equals to C2 V2. Others they write CI VI equals to CF VF, no problem. The first concentration is 0.63 multiplied by the volume is 50, it will be 0.05 equals to the second concentration is the one that we are calculating, and then the volume will be 1 dm cube, which is 1 in this case. Fine. If you use a calculator, you will find that now C2 equals to 0.01315 mole per dm cube. Fine. Now that is the concentration. 7.2.3 they say to us calculate the percentage purity. Now the percentage purity in this case of oxalic acid. Now where do we start? We have to calculate the number of mole of the sodium hydroxide that was involved in the titration. We are given the volume and concentration there. So the volume is 40 from this concentration. Therefore, number of mole of sodium hydroxide will be concentration multiplied by volume, which is the same as 0.0315 multiplied by the volume of 40 will be 0.04. So the answer will be 1,26 by 10 to exponent minus 3 mole. That's the mole that reacted in the titration. Now if we use the mole ratio, we can know the number of mole of oxalic acid now that reacted with this during the titration. Yes, the balance equation, according to this one, you can see the balance equation is 2:1. Therefore, the oxalic acid will be half of this one, 1.26 by 10 to exponent minus 3, which will be the same as 6.3 by 10 to exponent minus 4 mole. Now from here we move to now can we find with mole, you can find the mass of oxalic acid that involved in the titration, which will be C2H2 and then O4. This will be the same mass equals to number of mole multiplied by the molar mass, remember. Therefore the number of mole is 6.3 from the previous calculation times 10 to exponent minus 4 multiplied by the molar mass of this oxalic acid will be 90. Then if you use the calculator, we'll get 0.0567 or 5.67 by 10 to exponent minus 2. This will be grams. Now this grams, remember, is in the volume that was involved in the titration. The volume that was involved in the titration is 50. Now this is in 50. This one is the mass in 50 cubic centimeter. Now we have to find the mass in the 75, the original solution in the sample. Therefore the mass of oxalic acid in 75 cubic centimeter will be obviously this one, 0.0567 multiplied by 75 divided by 50. Therefore this will give us 0.08505 grams. This will be the mass in 75. Now we need, question was saying, calculate the percentage purity. Therefore percentage purity of oxalic acid, then will be 0.08505 divided by, out of the original mass, 0.25 multiplied by 100. The answer gives us 34.02%. That is the answer, which is almost 6 marks. And now the last two questions, they are saying to us in 7.3, they are saying solution of sodium ethanoate or sodium ethanoate solid undergoes hydrolysis in solution. Define the term hydrolysis. That's 7.3.1. We know hydrolysis is just a reaction of water with salt with water. Reaction of salt with water. Reaction of salt with water. That's the reaction of salt with water. Be careful, don't write when salt dissolves in water. That is incorrect. 7.3.2, the last question in this, it's for 4 marks. I say now, according to the question, how will the pH of the solution be affected by the hydrolysis of sodium ethanoate? Choose from increase, decrease, or remains the same. Use the balance equation to explain. So normally we can just say, if you write it down, just for clarity's sake, sodium ethanoate is this. So this is coming from a weak acid, which is ethanoic acid. This is coming from the strong base. So you can see now this sodium ethanoate is basic because the salt of a strong base and a weak acid. So the pH will be above 7, obviously. Therefore, we'll just now write the first thing, it will increase. The pH increases. As they say, write increase, decrease, or remains the same. Therefore, use the balance equation to write this one. To be honest, let's write the two equations. First, you have to ionize the salt. Ionize the salt, sodium ethanoate in water. It will form the ion, the acetate ion plus sodium ion. Now remember, in this section of hydrolysis, only the conjugate ions or conjugate acid or bases of weak acid or weak bases undergoes hydrolysis, or only strong conjugate acids or bases undergoes hydrolysis. So the conjugate, this one is a conjugate base of a weak acid, is strong. Therefore, this will undergo hydrolysis, whereas this one is a conjugate ion in this case of a weak acid, of a strong acid, strong base. Therefore, this one will be weak. Therefore, no hydrolysis, because we say only strong conjugate ions or only ions coming from the weak acid or weak bases. That's the simplest one. Therefore, acetate ion will undergo hydrolysis and then react with water to form, because this one is a conjugate base, it will accept the hydrogen to form the acid as ethanoic acid, and then after losing hydrogen, water will remain with OH minus. Therefore, according to this one, we say the solution, therefore sodium, this one, sodium acetate is basic or alkaline since OH minus is formed. That is the sign that is a base. That's the end of it. So you get, for this one, you get the 4 marks in this case. So thanks a lot. Until we meet next time. Bye.